Hey everyone, how's it going? Welcome to my stream. Today I'll be continuing to work on my Vectrex emulator called Vectrexy. Last week I was working on the implementation of the timers for that are used by the Vectrex. One of the timers is mainly used for drawing, and another one of the timers is the other timer is used for kind of like global timing stuff, the game frame timer. So yeah, actually since last week I did a little bit more work on this. I kept reading the documentation here over and over and realizing that I didn't quite get everything right in there, so I continued to work on this. Pretty happy with where it's going. Let me just see here. I think I almost pushed everything, so if you're interested in following with the changes, I'm not sure it's really worth going through these changes though. A lot of them are more cosmetic, although there is one that's kind of nice. Like I finally did some hold on a sec. Okay. Like one of the things that I did finally was start using constants to represent the different masks and stuff. And I wrote a couple of helper functions so that the code starts to read a little bit more cleanly. So here you can see what I do is, like for the B register. Hey ABCW, how's it going? Thanks for joining. So yeah, like what I did is I have these like namespaces for each of the registers in the VIA, and I just have a bunch of constants in each one. So these are just mapped to some bit masks or shifts or whatever. And what I do, like as an example, what could be a good example here? Yeah, like for the auxiliary control register, bit 5 controls timer 2's mode. And what I do is I use the name of like the mode that is enabled if it's 1. So like, yeah, actually I realize this is inverted here. Comments lie. ABCW says, not bad, my Win 10 PC drive got corrupt, so I spent the entire weekend repairing and reinstalling Windows. Ah, that sucks. I hope you had all your shit backed up. Yeah, my weekend was pretty good. Didn't do too much. I did work a little bit on this though, so that's pretty cool. I don't get that much time to work on my personal projects outside of my streaming hours, but when I do, it's good, you know. Nothing important. Okay, that's good. It's good to hear that you didn't have important data on your drive that you lost. So, yeah, so here, timer 2 pulse counting. So if it's 1, it's pulse counting. If it's 0, it's one-shot mode. Here, bit 6 controls timer 1. If it's 1, it's free running. If it's 0, it's one-shot. And then, like, I have these little helpers here, like get timer 1 mode. If you pass it in, I just check, you know. Oh, and also I started using these are some functions. I actually wrote these for my NES emulator, and I decided to bring them in just because it reads nicely, rather than just doing a whole bunch of bit masking and stuff like that myself. I have some little helper functions like set bits to 1, set bits to 0, or set bits to enabled or disabled based on the mask you pass in. Read bits with shift, test bits, which is the same as reading, but just to returns true or false. Stuff like that. Just, you know, nice little functions that kind of help with readability. So then you get code that looks like this, like get to timer 1. Get timer 1 mode is I just test the bits in the auxiliary control against this bit mask here, which is really just 1 bit, bit 6. And if it returns true, then we're in free running. Otherwise, we're in one shot. Similarly, for timer 2, I check if it's timer 2 pulse counting, so bit 5 here, and if so, then we're pulse counting or one shot. So then, you know, lower down here, I'm able to do things like assert values and stuff like that. So it just kind of makes it look a bit more clean when dealing with with bit masks. Also for shifts, like here in port B, bits 1 and 2 are used for determining which of the 4 outputs the mux is going to choose. So I have here the mux selection mask, and I have also the selection shift, which really is just the low bit here, but whatever. And then what I do is I have, like down here, if the mux is enabled and I want to know which of the values 0, 1, 2, or 3 it is, I say read bits with shift on port B using the mux selection mask and using the mux selection shift. So that just reads out those bits, and then I can check if it's 0, 1, 2, or 3. ABDCW says, your streams really got me interested into emulators. After I finish studying C, I'm going to work on a chip 8 emulator. Yeah, that's a great idea. That's an awesome idea. I never wrote a chip 8 emulator. I jumped right away into NES. But granted, I had quite a bit of experience programming in C++ and writing games and stuff. So it's not necessarily like a good idea, I think, to start with NES emulation. I mean, maybe I'm wrong, but I think it's pretty complex. I think chip 8 is a nice stepping stone. ABDCW. Oh, Repnop. Repnop says he should check out the doing Game Boy emulation. Yeah, Game Boy emulation is pretty nice. It's simpler than NES. You know, just because like you don't have to worry about color output and all the weirdness of the NES. There's a lot of weird stuff about NES. On the other hand, the Game Boy has its own challenges that the NES doesn't have. Like I know the CPU is more complex. The CPU is more complex, and actually the documentation that's out there is a little less good than what's out there for the NES. The NES is like more documented. So yeah, but definitely a good idea. So yeah, so I did a bit of cleaning up here. Now, where was I here? So yeah, I was reading about like how if we focus here on timer 1, which is this one here, that's the one that's used for drawing. It's really, really important that I get this one implemented correctly in terms of timing, because everything about timer 1 is controls vector drawing for the most part. Like most of the BIOS vector routines are the kinds where we say like, I want to draw a vector, so we turn on the beam, and it's basically the beam is tied to the time of timer 1. So if I don't get this right, then vectors really don't draw properly. Repnop is talking about checking out Rust. It's definitely on my list as well to check out. I find it really interesting as a language. The idea that it like helps you with your memory management, and that whole idea that they can guarantee, what is it? They don't guarantee that you won't leak memory, but they guarantee that you won't have like legal access to memory if you stay within the rules. So like no dangling pointers type stuff, like no access to dangling pointers. Oh, is there someone making a Game Boy Advanced emulator in Rust? If that person's still active, I'd love to follow that. Repnop says, yeah, memory safety. Memory safety guarantee. Leaking memory is completely safe though, right. Yeah, not the case with C++. Although, the way I write it, it's generally the case, but I cannot guarantee it in the same way because the compiler won't help me in the way Rust compiler will. ABDCW says, no, I don't think he is. I think you kind of hinted at that last stream, following people who do emudev. And I was saying there are not really that many, unfortunately. I mean, of course, there's Ferris. Okay. Yeah. Well, hopefully more people will get into streaming emulation dev. Repnob says, I've heard a lot of safe C++ 14 and beyond, or sounds like a bit of a pain, or whatever. Oh, I don't know. I mean, if you watch my stream, it's not too bad. Although, to be fair, I'm not doing like a ton of allocations and stuff. Because that's the thing, right, with emulators is, you know, at least these kinds of emulators, like old school hardware, you don't really need to do lots of allocations and stuff like that, right? You kind of like set up everything at the beginning, allocate everything up front, and kind of done after that, right? But, you know, like what did I do? Here you go, make unique. There's a memory managed shared pointer, or here unique pointer. So I don't have to call delete on it. I don't have too much of this, I think. I do have it in a couple places. Yeah, I have it in the CPU because I've got the pimple idiom going here, just so that I can keep the code a bit more clean in the CPP file. But yeah, emulators like this are not really a great example of where you get the benefits of all this. They're kind of easy to do in terms of memory management. So yeah, I'm gonna keep working on this. One of the last things I was reading about timer 1, and I'm like trying to figure out what's the right way to do this, is I was thinking about this here. It's the idea that we work here in one-shot mode. Let me just get to that bit of information here. So it's like the timer 1 one-shot mode generates a single interrupt for each timer 1 load operation. And as with any interval timer, the delay between the write to timer 1 counter high operation and the generation of the processor interrupt is a direct function of the data loaded into the timing counter. So yeah, in addition to generating a single interrupt, timer 1 can be programmed to produce a single negative pulse on the PB7 peripheral pin with the output enabled. With the output enabled, a write T1CH operation will cause PB7 to go low. PB7 will return high when timer 1 times out. See, this here is the key, right? This is how the Vectrex manages the vector beam. So basically, when you want, or anyway, it's the main way that the Vectrex manages, or like how people programming the Vectrex managed their drawings, is to say, like, I know that the vector beam is pointing somewhere right now and it's not drawing yet, like it's not turned on, and I want it to turn on, and the turning on of that is actually managed through this PB7 output here. It's actually connected to the ramp. The ramp is what controls turning on and off the beam, and if you pull the ramp low, the beam turns on, and if you pull the ramp high, it turns off. So this timer is connected to that. So if you have this enabled, this bit here, the output enabled, you then start your timer by actually writing to the high portion of the counter, and it starts counting down. But immediately when you write there, or not quite immediately, it looks like 1.5 cycles later from what's here. So yeah, like literally 1.5 cycles later, it pulls PB7 low, so it outputs a low signal, which turns on the beam, right? And the integrators also turn on and start to move the beam. And then, as soon as the timer is done, it turns off the beam because it pulls PB7 high, which turns off ramp, and then we stop drawing. Now, for me, there's like two things I want to handle here. I'd like to ideally handle the 1.5 cycle delay, which, I mean, I can't really do the 0.5, but, you know, let's say 2 cycles. I think, I don't know how important it is. I'll definitely make a note about it. But more interestingly is what I want to make sure I do, because like if you look here, yeah, so I have this update function, right? And I'll be updating my timer 1 like this. The thing is what happens, like, let me just open a, like, let's say, you know, there's like only 3 cycles left before the timer would turn off PB7, but I get an update of 10 cycles, right? So like this would be 3 cycles, and you know, and so I would update it with 10 cycles and find out, oh, I'm supposed to turn it off after 3, or I wouldn't know anyways right now. And I want to make sure that I don't move the beam ahead 10 cycles worth, but only 3 cycles worth. And I don't want to say, like, I have 3 more cycles to move the beam, but because I've updated with 10, it says, oh, PB7's done, so don't advance, or like don't keep integrating, don't keep moving the beam, and then all of a sudden my line is cut short. Right? So I'm actually, it's going to be very important for me to get back from the timer how many cycles until PB7 is turned off. So, you know, there are different ways I can handle that. I can either do it here, where I kind of, you know, update, maybe pass in something or return something, or query on the timer one to get the info for this. And or I can kind of like do it with a sort of callback, you know, which would be kind of like more the realistic way the hardware would do it, because there would be an interrupt. But I don't think I'm going to do it that way, because first of all, it's a bit expensive, and secondly, it's not like we're in real time drawing. I need to draw here, so I have integrators here enabled while ramp line is active. Now, this code is commented out. It's going to come back, but it basically gives the general, you know, the way it's supposed to work is we check if the ramp is active, and if so, we go ahead and we move the beam. So that's exactly what I was saying. It's not just is it active or not, it's how many more cycles will it need to be active. So that's what I need to figure out here. So that's one. So yeah, let me just take a few notes in my code here. No, not here. Oh yeah, and another thing I was reading about here is that there's the difference between the interrupt flag and the IRQ pin, which, you know, I've been treating as one, but from what I'm understanding is that there's a mode in which the timer can run where the interrupt flag kind of gets set, but the IRQ pin is not affected. Let me see here. One thing I don't understand here is it says here, as with any interval timer, the delay between the write to T1 counter high operation, the write to that operation itself, and the generation of the processor interrupt is a direct function of the data loaded. Like the delay between this and the generation of the processor interrupt is a direct function. Oh, okay. Okay, they just mean that that's what timers do. So I thought they were talking about here is PB7, but that's not what they're talking about. In addition to generating a single interrupt, timer 1 can be programmed to produce a single negative pulse. Okay, so I think I'm actually handling that here, PB7 here. So when we write to the counter high, yeah. I think what I need to do instead here is, rather than do kind of like PB7 enable, what I want to do instead is maybe store what? Thinking like store the number of cycles that it's been enabled for, or when we update. Yeah. Not sure yet. I'll get there. Let me just keep reading here. The output pin enabled and cause the PB7 to go low. Return high when timer 1 times out. So that's kind of what I'm doing here. I'm calling it PB7 enabled. I'm not sure that's what I want to call it. Maybe what I really want to call it is high, low, or number of cycles that's high or low. So we'll see. T1 interrupt flag will be set. The RQ pin will go low. Interrupt enabled. Yeah, that's another thing too, is there's also the interrupt enabled that I have to handle. So let me just check that for a sec. Interrupt enabled. Timer 1 interrupt. So these bits here might also be checked. See, there's the interrupt flag versus the interrupt enable. Not the same thing. Even though they are tied together. It says the T1 interrupt flag will be set, but the thing is, because you can reset the interrupt flag independently. So T1 interrupt flag will be set, the IRQ pin will go low, interrupt enabled, and the signal on PB7 will go high, which is disabled. At this time, the counter will continue to decrement at system clock rate, which I'm doing here. This allows the system processor to read the contents of the counter to determine the time since interrupt. However, the T1 interrupt flag cannot be set again unless it has been cleared as described in this specification. This documentation is not super clear, but that's why I keep rereading it. Every time I read it, I like extract a little bit more information. And I finally understood what this here. This is the phase 2 clock. And each one of these here is basically high, low is 1 cycle of this clock. And then here, this is just 1. So that's why this is 1.5. So it says write to T1C high here, and then that takes, well actually that's 1 cycle here. So I don't know why it says 1.5. Let's see, low, high, low, high, low, high, low. Okay, the extra cycle, half cycle comes at the end here. So ABDCW says, how does this system display graphics compared to other emulators such as NES, other than the fact that it's a Vectrex? Yes, RepNop, it is vector drawing. That's exactly right. It's really interesting actually. Basically, unlike the NES and all raster displays, it's not raster based. I mean, it is just a television. In fact, the Vectrex is a TV turned on its side. So it's, taller than it is wide. And you have control over the vector beam. And the way that works is you don't set like the XY value you want. In fact, what you do is, what you're mainly controlling is like they call it, like they have different names for it, but you're driving the integrators for X and Y for the beam. And so what you're setting is like a strength value for X and for Y, which range from -128 to 127. So that also determines the direction, right? So like if you want the beam to go as fast as possible from the left edge of the screen to the right. Now let's say the beam is already pointing to the left edge. From there, to get it to the right, you set the X integrator to 127. And what you want to do is you want, in fact, this timer 1 that we're talking about here, you'd want to make the timer have a maximal value in there. So it would be 255. So it would count down from 255 down to 0, and that would make the beam move across the screen, ostensibly writing, like you could think of it as writing 256 pixels across the screen, which would, because actually the display is a 256 by 256 but not square display. It's in 3:4 resolution, but internally you can think of it as a linear 256 by 256 display that is like not square. So knowing that, you can basically draw vectors that way, and you have to program it by kind of, one of the things you do is you reset the beam to 0, 0. That's one of the things you can do. So that there's actually functionality in the hardware where you can say, I want you to bring the beam back to 0, 0. And then from there, you do relative computations. So one way to think of it is, for every object you want to draw on screen, you consider an object as, let's say, something made up of like 5 or 6 or 10 vectors, right? In your code, you're tracking its position somewhere, its center, and maybe its rotation if it has one. And so what you do is you say, okay, bring my beam to 0, 0, move to like the first vector I need to draw for that object. So move there with the beam turned off, turn on the beam, start drawing my vectors. And typically it's a closed shape. Then after that, you typically want to bring back your beam to 0, 0 and then move to the next one. And the reason you want to do that rather than move to the next object's position is that if you don't, the beam will drift. The beam apparently drifts quite a bit. If you don't zero it enough times in a frame, I read, what was it again? It's like it can drift centimeters, a few centimeters every 10,000 cycles. And you have about 30,000 cycles to do your whole frame to keep it at 50 hertz. So that's basically how the Vectrex works, and how like most vector displays work apparently. Not that I know, but this is what I've learned about how Vectrex works. And so yeah, all of this is related. This timer here, it's actually called the scale because it kind of controls the scale of your vector. But it's really not the scale, it's the time at which your beam is drawing for. So it's like this weird combination of timing and strength that you put on your vectors. And what I keep reading is, prefer to use larger values in your X and Y integrators, like the strength to move your beam, and smaller times so that you can do more vector drawing in your 30,000 cycles you have, right? Because there's like two ways you can draw the same length, or multiple ways, not two ways. You can draw your same length line by playing around with how fast your beam moves and how long you let it turn on and off for. So obviously lean on making it move really fast, the beam, for less time, and you'll be able to draw more lines in one frame. So sounds like the people programming for the Vectrex really had to master the timing behind it, And from what I read, I think most of the games were programmed by one person who worked for the company GCE, the ones who made the Vectrex. I think he got really good at it. I also learned something cool. One of my favorite games on the Vectrex is actually a game from Konami. So the game is it's called Scramble. I'll show you a video here of the game on the Vectrex. maybe this one here. Maybe not. Yeah, scramble. See, it looks like this. Yeah, I'll put the audio on. There we go. So scramble is like you're controlling the ship, and you have like this fuel line, and you gotta shoot these square fuel tanks at the bottom, which refills your fuel line, and there's kind of like 4 stages to go through. So I love this game. It's one of my favorite games on the Vectrex that I would play. And I learned that Scramble, if I look here, Scramble arcade game, here's exactly the same game. And you can see here Konami 1981. And I'll just go ahead a bit. And you have like... So it's the same game, of course it's with bitmap graphics and sprites, although the terrain is clearly drawn, you know, using some kind of, I'm not sure, but they're basically like doing kind of a 2D terrain drawing here. In fact, I suspect the way it works is that the raster here, it's the same idea where the screen would have been flipped sideways, so the raster is probably moving from top to bottom, and they know that, you know, either through cycles or interrupts, when they reach the point of the terrain where it becomes terrain, and then they'll draw like a couple pixels in one color and then the rest in red, something like that. And then this is just a sprite. Oh, too loud? Sorry, man. I can't exactly hear it, so... Better? Yeah, actually, I guess it makes sense. I'll want to make the sound approximately like what I can hear from playing from Winamp. So yeah, so this game here is from Konami, and basically Vectrex, the GC company, licensed the game from Konami so that they could code it themselves. And there it is.
And here's those infamous UFOs I was hearing about in the game.
Thanks, Rob.
The thing is, they will actually kind of follow you in a certain path. They try to corner you and just smash right into you.
So yeah, so that's Scramble. So that's pretty cool. Okay. The T1 interrupt flag will be cleared. The contents of the load or latch will be transferred, and the time will begin to decrement as the system clock rate. So this I already did. If the PB7 output is enabled, this signal will go low on the O2 following the write operation. See, that's okay. So it is one cycle later that I'm supposed to do that, and I'm not really doing that right now. So, okay, what I'm going to do here, wrong place. I'm going to do this. I'm going to have the interrupt flag, and don't know. Should I go with a bool? Should I go with an int? Let's do something like this. And similarly, I actually don't know if I have to make this mutable or not. We'll see. PB7 signal low. Because actually there's, maybe I'll call this flag, PB7 flag. because we can control these independently as described here. ABDCW's got some work to do. Oh, thanks for hanging out, man. All right, so let's see here. Okay, this is register addressing. I think I have it here. Okay, so this enables or disables the PB7 output. So this is basically the flag we're talking about here. It's controlled by bit 7 in the auxiliary control. So let me see if I've got that hooked up. Let me just undo this here. There we go. PB7 enabled. Right. What I need to do is if we get a write into the auxiliary control. Okay, that's a read. And I have the part here where we do writes. So here, what we do is we write the value here, then I check timer 1 mode, set that on timer 1. I also need to set whether PB7 is enabled based on the value now of that register. No, that's not right. That's actually the flag. Okay, so I need this function. I'm avoiding calling it enabled internally like I did before because it's confusing, right? Because we have the concept of PB7 being enabled, the concept of it being enabled when the signal is low versus the flag being set. So I'm just going to do that. So I'll keep the name here in the concept, but internally I'll just store it as a flag. Right. Timer 1. So that sets it. I need to also get it. Which what was I doing here? Yeah. Okay. similarly. I should probably just make a function for this. So if PB7 enabled, and in fact I think I had this wrong. No, it says it not equal to 0. No, that means that then I had it right. Then we set the ramp here. Yeah, no, this is not right. This is the part I'm gonna need to fix based on timer 1, and yeah, this is wrong. We need to account for how many cycles PB7 was enabled for before we turn off drawing. Okay. But if I come back here, when I read auxiliary here, I need to update its values, which I'm not doing at all. Which basically makes me wonder if I even want, one of the patterns that I've been seeing now is, like here I ended up commenting out my timers, because in fact all of this data is stored directly in the timer. But here I have like kind of like a flag register, and the question is, do I build it on the fly? Probably that's what I want to do. And do I even want to cache the value at all? PA, PB, latch enable. I don't think these are ever even used. This here will control how shifting works. That'll be probably set some internal variable. And then here, these 3 bits are all related to the timer, which makes me feel like we don't really want this guy here. Yeah, I'm thinking no, which will change a bit the way I've written some code here. So rather than set this value here, in this case we'll just check the value, and then we'll update our timer 1. We're going to end up updating timer 2 as well. So that's good. And then for returning it, Alp143 asks, what are you developing? I'm writing an emulator for the Vectrex, which is a console from 1982-83. Alp143 says, that's awesome. I need to learn C, C++. I'm from Python. Oh, that's a good starting point. Python's got some core similarities to C, C++. I write some Python at work. Oh, let me put back my music. If you guys don't mind, I like to have a little music. So what do I want to do here? Right, I need to set timer modes and all that. Oh, do I have it on my timer 1? I'm not storing because it's right now I'm only supporting one shot. So I don't have a timer 2 yet, but it'll look something like this. Set PB7 enabled based on this here. So like, it's not great having to build masks and stuff like that, but at the same time, this is probably not accessed too often per frame. So not too worried about it. So we'll see how this goes. The other option is, like I was saying, is to kind of cache the value in a data member and only update it as needed. So if that would be an optimization. The thing is, I prefer not having to cache, because caching is, you know, having your data in multiple places is the greatest source of bugs. So I try to avoid that as much as possible. Basically redundancy. Avoid redundancy. Repnom says, I might start streaming Barnacle Boy development to force myself to work on it. You know what? That's a super good idea, because actually, since I started streaming, I work way more on this emulator. And I have a great excuse, you know? Like sometimes I'm tired and I'm like, oh, you know what? Maybe I'll skip or something. But then I'm like, you know, it's kind of just don't want to like skip too often, you know? And so I'll put in my couple of hours, and then once you get into it, you know, it's cool. Get some work done. Okay, and then here I wanted interrupt flag. Can we set the interrupt? No, see, that's it. Interrupt flag is set internally, so we never have a set on the outside. So that makes sense. We can control whether the PB7 output is enabled, but yeah, this is just confusing. I'm gonna change this to flag. Here, I'll use rename. I'm wondering if I should also rename Okay, let's say we rename this too. It's a nice feature of Visual Studio 2017 to be able to rename in C++, and it works quite well. I think it's in 2015 as well there, but okay. And then the other thing I wanted to expose is Rapnob says, I'm going to head off for the night. Have fun. Catch you later. Hopefully I'll be able to catch one of Ferris's streams soon. Always ended up doing something. Yeah, I'm actually at work when he streams. And so I have to like sneak myself watching it. And it's like, it's always when he's streaming that somebody schedules an impromptu meeting or something. It's kind of funny. I mean, my work doesn't really care. You know, as long as you get your work done type of thing. But still, you know. Anyway, thanks for hanging out, Repnot. Hope to catch you next time. See you, man. Okay, so this will change the code and update. This is gone. So instead of testing bits here, we'll actually check the timer itself. That's it. If the PV7 signal is low, and I kind of like this because it's a bit more clear what's happening here. We see clearly that the whole ramp thing has to do with the timer 1. And likely even this here will disappear and I'll control directly like I might want to abstract. I sort of have like the basis of an abstraction for the display itself. Do I have it here? No. Where did I put that? Here, this thing here. I have a very basic abstraction for the display. I might want to have like, we'll see. I don't know. I'm thinking something like in the VIA we have this abstraction of a vector display where you can turn on and off the beam and, you know, move the thing. I'm not quite there yet, but if that's the case, then I'll be driving the whether the beam is on or off rather than setting a bit here. So we'll see. All right. Let's get this compiling. What is it? It doesn't like here. Cannot assign to a variable that is const. Right. Right. I think same thing is going to happen with my interrupt flag. It's going to disappear. Rather than do this, I'll construct it on request. Number 1 set. Oh, so we can set the interrupt flag. Yeah, of course. Here, bit 6. Okay, so I was wrong. I do need a way to write to the flag. Yeah. Alright, so set interrupt flag to let's test the bits in value, the input guy, for the bits, it should be bit 6. Yeah. So we do that. Oh no, sorry, this is the return value, read. It's not, this actually is not the right thing. Instead, do this. And we query like that, and then we return interrupt flag here. And then this set will move into the place where we write. Right, interrupt flag here. So actually I'm going to put back my, yeah, no, I'm going to do this like this. This disappears. Handle setting all other interrupt flags. Okay. So that's good. So I don't need to do this anymore, which is good. So all this disappears. So let's clean up a little bit and let me get this committed. Okay, so this builds. Should also run, although it doesn't do much. Still not drawing yet, but getting there. See, if I could just turn off the trace. So there's the render, which of course is not drawing anything just yet, but we're getting there. And look at my diff and beyond compare. interrupt signal. Yeah, I'm not sure yet. I'm gonna leave these in comments just for now. I will eventually delete them though. Ah, okay, so this can disappear. Okay, this all looks good. Via more timer 1 refactoring implementing. All right. Oh yeah, and I wanted to put a little to-do about waiting a cycle. Because as it says here, when we write to T1 to timer 1 latch high, no, sorry, not there. Timer 1 counter high. Where is it? Basically here, we write the timer 1 counter high. We have 1 cycle before any of this happens, before the IRQ changes. No, sorry, before PB7 goes low. As for the interrupt flag, I think it does get reset right away. It's here. It's if the PB7 output is enabled, this signal will go low on the O2 following the red operation. So yeah, it's not quite right what I have here. I need to separate the concept of the signaler. So I'll say it's like this. It's not that this becomes true, it's if and PB7 flag, then PB7 signal low becomes true. But the to-do here is that this has to happen 1 cycle later. This should happen 1 cycle later. Okay. And then when timer run expires in the update function, this happens. When the counter reaches 0, the T1 interrupt flag will be set. The IRQ pin will go low, interrupt enabled. And the signal on PB7 will go high, which is what happens here. However, the T1 interrupt flag cannot be set again. So actually the flag doesn't get touched. So this is more correct. So I'm not going to implement free run mode because I don't need to right now. So okay, I think this makes more sense now. So technically this would happen one cycle later, which is totally doable. But I see then I end up dealing with the same problem. I have to be very careful about when I start drawing and when I stop drawing. Right now I'll be drawing potentially one cycle too early. No, actually I'm going to have the opposite problem that I described earlier about stopping to draw too late or too early. And then for drawing is if more cycles have elapsed, I should have already started drawing. So I need to like track how many cycles or at which cycle. That's what it is. It's kind of like I need a timestamp. Like when did the signal go low? When did the signal go high? So that I can draw correctly for that many cycles. Yeah. Otherwise, you know, my lines will be totally the wrong length and will be dependent on my frame rate. It will be dependent on which instruction got executed before, how many cycles it took. Because basically, if every time I execute one instruction, I get how many cycles, and then I update the VIA with that. So if somewhere in between there, the PB7 flag got set, there's a certain number of cycles afterwards that I need to consider, like I need to have already drawn. I need to draw that much for that long. And similarly, if in the middle of those cycles when we're done drawing and the signal goes back to high, like over here when we're done, I need to know how many cycles before then so that I can draw the last bit of the line and stop, or move, draw and move there. No, it's actually for drawing. So yeah. I need to get all of that correct. It's basically the problem of dealing with analog movement in a digital environment like this with variable delta times. So let me see if all this makes sense. PB7 flag here is controlled through here. So completely controlled externally. That makes sense. PB7 signal gets set to true here and false there. That makes sense. Interrupt flag will get reset if we write here. It also gets reset if we read here, as the documentation says. When expired, the interrupt flag gets set and the interrupt signal goes low. But what resets the interrupt signal? That's the bit I'm missing. Generates a single interrupt for each timer load. What I'm not sure about is what gets the because this is one-shot mode and it talks about this single interrupt, generates a single interrupt for each timer load operation. But they don't describe what pulls the interrupt signal back to high. And I wonder if that's because it's something that gets pulsed rather than stays in one state. Let me see if Wikipedia has anything to say about that. I think it's here. In one-shot mode, each timer continues running so that the time since 0 was reached can be determined, but no further interrupt is issued. Yeah, it's really a one-shot thing. When it reaches 0, and timer 1 can also output pulses. I guess the thing is I don't know what the interrupt is used for. So even though I have this logic to pull it low, I don't know yet what we're using it for in the Vectrex and how it hooks up. So what I'll do is I'll just put a to-do here. When do we set this back to false? What is it used for? Don't like that formatting, so I'll just do this. Okay. So what I'll do with this is I'll actually amend my previous commit with it. So I think that's enough for timer 1, and which is great. Now I should implement timer 2. I kind of have like two choices at this point. I can implement timer 2, which is the one that's used as the game frame timer, or I can fake it for now and just like always return that timer 2 has expired in here, which basically would mean that whenever the game says, you know, wait until timer 2 has expired, it'll expire immediately. So it'll run faster, right? It won't run at 50 Hertz in real time, which is probably fine for now. And if I do that, then I can focus on the drawing logic, which would be more interesting. Yeah, let's do that. I also wanted to move this code for the timer out of the VIA header file. Yeah, let's do that at least. This would be a good idea. So add new item, header file. Source, I'll call this timers. Move timers to new header file. Okay, so basically what I was saying for timer 2, in order to fake it, it's here, it's when we read. Here. So eventually we want to do something like this. Oh no, not this. It's D here. It's the interrupt flag. For now, I'm gonna put here hack. For now, timer 2 will always report that its interrupt flag is set. This will make the game run faster than 50 Hertz. So if that's the case, now we should no longer get stuck. Yeah, there we go. We're no longer getting stuck in this infinite loop where it was waiting for that timer to get set. Okay, so now I can get to the interesting part. But before, I just need to go to the bathroom, so I'll be right back. All right. So let's see. I'm thinking what I'll do. I'll ignore the timing issues I've been talking about, which what I want to do is I just want to draw these lines, and I expect them to be off. I expect them to be completely off and all that, but I think we'll see like a general shape. If it's correct, if the logic is mostly correct, we should see the general shape of the lines we expect to see, which would be awesome. If we see that, that would be really cool. And then after that, we can focus on getting it to be cycle accurate. Yeah. So look at my notes. Yeah, so I took some notes. Basically, when I first wrote this code, I was using the code from internal.txt, which had these equations that described how the beam moves based on the inputs into the DAC. But you know, I thought about it and I don't think it makes sense to implement those equations, because that's really just explaining like literally how the hardware, you know, based on voltages, how the beam has to move, like how much voltage it requires to swing it. But the equations are linear. There's a linear mapping for the most part between the inputs that we set, like the strengths that we set, and how much the beam needs to move. And since we're working in screens, like in an actual pixel buffer in OpenGL here with a fixed size, we should be able to just draw our lines. Yeah. And what I was saying earlier about how the screen is 256 by 256, and what I read was that to draw a line that covers the full span, you need to set the X integrator strength to 127. So actually not FF. Yeah, exactly. 127, let's say, in one direction. It will be minus 128 in the other. So close enough. And actually, anyway, but basically, if we were to set, let's say, to go from the left edge of the screen to the right, if we had our beam already at the left edge, we'd set the X integrator strength to 127, and then scale T1 to 255, which means set the timer to FF, and it would basically draw for. It would take 256 cycles at full speed and scale to draw a 250. Well, I said plus scale, no, full speed really, to draw a 256 pixel line. I paused for a second because I remembered that I did not actually implement some of this logic correctly for setting the integrators. I was focused on the timers, but this crap code that I wrote with the go-to, this needs to be fixed. Yes. Well, yeah, what I remember is that what I have wrong here is that in fact what I call here velocity.x here actually gets set every time we write to the DAC, not just if the mux is enabled or not. Okay, so what we're gonna do here, we're gonna get rid of this goto, and we're gonna write ourselves a little local function. If the mux is enabled, we do this, remove the else here, always output to the x-axis integrator. But if the mux is enabled, then we write specifically to the one we want to write to. This offset thing, though, yeah, I need to take that into account. Yes. That's the brightness, which I'll ignore for now, and this I'll do later. Okay, so we have this nice little function. And so now, rather than this crap, we can do like that. Okay, so I think that's right. If we write to A, which is the DAC, we need to update our integrators. Same thing for writing to B, because B controls the mux. So in both cases, we update our integrators, which will come into this function here. Just make this a little bit less terse. More terse, I mean. Okay. So that should work. So now let's do this. So let's think about ramp. It's not just if the PB signal is low, it's also if it's enabled. So if the flag is set and the signal is low, we disable the ramp. And the reason why I need this is because this actually can also be set directly on port B from the processor. That's why I care about this checking still on this port. Okay. So integrators are enabled while ramp line is active. So instead of doing this, I'm going to use test bits. Port B. Okay, integrators are enabled if the ramp is not disabled. Okay. I want the autocomplete work. Integrator. Should be integrators. Okay, so now I need to figure out. I'm gonna put 128 actually. Oh, that's it. Divided by this. I have to be careful because this might be 0, in which case I need to not do this. Alp143 asks, how difficult is it to program an emulator? Laugh out loud. Yeah, it's not easy. It's not easy. It's fun though. You learn a lot. For me, I've been learning a lot about hardware. For the Vectrex, this is the most interesting part for me. Learning about the vector display. Actually, I wonder if the XY offset is just something I'm supposed to subtract. I think it is. And I may need to do the subtraction here because these values are going to be 0 to 255 if I'm not mistaken. Yeah. So this gets me the value, the direction value, assigned direction value. Shifts it basically into the signed range, minus 128 to 127. This here gets me the magnitude, the strength, as a ratio, multiplied by the number of cycles. And now my question is about this offset, which is also needs to be shifted. Yeah, I guess I could just subtract it from the value. Before I multiply by the cycles. How close am I to being done? I'm not sure, actually. I mean, right now, I've got most of the CPU implemented, and I'm doing the display part. Now, if I get this working soonish, and I've got display mostly working correctly, then there are some, like, you know, enhancements I'd like to do to the display. Like right now I'm just going to be drawing lines in OpenGL, but ideally I'd like to do something a bit nicer than that. Probably in a pixel shader. So anyway, that's an enhancement. And then there's audio. And I need to also pull input, which shouldn't be too hard. But I do need to emulate audio at some point. So I don't know. Still probably a few months of work. I mean, at the rate that I'm working on this, which is mostly twice a week when I'm streaming. Sounds complicated. Do I recommend C or C++? I come from Python and some Java. Well, I mean, I recommend C++. Especially if you've come from Python and Java. C, C++ is effectively a superset of C. And you can do more with it. Does this make sense? If I use C++, what projects are good to learn it? Like, what is C++ best for? I know it's general purpose. So to answer, I'll answer your second part of your question. What is it best for? C++ is good for pretty much the same things C is good for. It's a low-level language. It's a systems programming language, right? So what that means is that it's a good language to write code that is close to hardware. Gives you access to hardware. So most hardware, anything that you can drive that's connected to your PC will often provide some kind of API. Usually the API will be in C. So you can use C or C++. Below C and C++ is, assembly. It's kind of like one of the closest languages you'll get to assembly without it being assembly. It's actually a higher level language than that. And today, another language that's like that is Rust. So that's another systems programming language. Now, as for what projects are good to learn it, well, I mean, I think personally writing games is a good way to learn C++. There's a lot of stuff out there, a lot of great tutorials. You know, there's a bunch of tutorials that you can learn if you want to learn SDL. Like, the simple direct media layer. So basically this is like a C++, no, sorry, it's a C API. So CSDL is written in C, works natively with C++, and actually there are bindings available for languages like C# and Python. So actually that might help you, because if you look at examples in Python and get to learn the API and kind of move from that to C++, maybe that's a good path for you. And what's nice is that, if I remember, there's some nice tutorials, maybe on the wiki or something. Tutorials, yeah. I mean, I don't know if this is a good intro to C++. Definitely a good introduction to how to use SDL. But honestly, if you want to learn C++, I think one of the best ways is get a good book. There's actually a nice thread on was it what was it? Stack Overflow? Like best C++ books. Here, the definitive C++ book guide and list. I'll paste that in chat. So basically this post here, the top post, goes and gives nice introductory books. And you'll see here, like, the top book here for introductory, no previous programming experience, is this book by Bjarne Stroustrup, and he's the guy he's the creator of the language of C++. And then he has here introductory with previous programming experience, some best practices books, in intermediate level, advanced level. So yeah, I mean, I don't know if you're probably more somewhere in here, right? I mean, I don't know if I completely agree with this book up here being for no programming experience at all. Being good for somebody only with no programming. I think this book is good. Yeah, it says here, but is not only for beginners. It assumes no previous programming, but it's not only for beginners. So this is useful even if you have some programming experience. Alp asks, I have a book. Is C++ good for desktop apps or basic software? I'll say yes. C++ can be used for many things, including writing desktop apps. Many desktop apps are written in C++. Although less, I'd say, these days, right? With powerful computers and cross-platform being a thing and web being such a big thing, I see a lot of people writing, desktop applications now in JavaScript, using what's it called? That desktop JavaScript thing there, whose name escapes me for some reason. I know Mattermost is written in that. Forget. Oh, it almost came to me. Electron. That's it. this thing. So you build cross-platform desktop apps with JavaScript, HTML, and CSS. So it's basically like running a browser in a window, but it gives you like many more desktop APIs and stuff that you can use, and it's cross-platform by virtue of the fact that it runs effectively in a browser. So that's what a lot of people are using today. Java has also been classically good for desktop applications because it's cross-platform. But then again, a lot of stuff is still written in C++, like Adobe Photoshop, for instance, Max, Maya, like editors like that. Word was at least originally written in C++. So C++ is good for low-level stuff. Essentially, maybe I should program a basic emulator then for a project. Yes, you could actually. Somebody earlier was mentioning Chip 8. I think it was ABDCW was saying that he wants to write a Chip 8 emulator. So Chip 8. So Chip 8 is actually like a fake hardware. No, not this here. Maybe I'll just look up Chip 8. See, here you go. Chip 8 is an interpreted programming language. It was initially used on the Cosmic. Chip 8 programs are run on a Chip 8 virtual machine. It was made to allow video games to be more easily programmed for said computers. Oh, interesting. I didn't even know that was a history. But basically, it's a really simple, low-level language that a lot of people use as their first foray into writing emulators. Like very simple instruction set, which is all here. And then there's a whole bunch of programs that have been written in Chip 8. So once you've got your basic emulator going, you can actually run these games and make sure that it works. So that's something you can look into if you want to learn C++. Maybe that's something you can try. The thing that's bothering me about the offset is we're subtracting 128 from it. So what I'm wondering is, would someone set the offset to a value that's negative? And if so, then that would basically be adding a negative here. And actually, if our value was negative, and we're subtracting a positive value, we just make it more negative. So I don't know, this doesn't seem right. You know what I'm going to do is, I'm just going to ignore this for now. Because in any case, I don't think it's set very often. I know that it's set to scale the graphics on screen, like in the case of when the ship moves down in asteroids, in Mindstorm, I should say. But generally speaking, it shouldn't be set. So I'm just going to ignore it for now. And we'll worry about it later. All right, so let's say we're doing this. The next thing to check is drawing enabled, like as I was doing over here, or do we just want to move? So now I do need, yes, to set my target position. I'm trying to remember what I did. Oh yeah. To flesh out my little Vector 2 implementation at some point. So we move, definitely, but before we do that, we gotta find out about drawing our lines. Blank. There's something about blank. Oh yeah, that's kind of important. The shift register. Oh yeah, I can't actually get the drawing to work properly without doing the shift register stuff. Okay, so I'm gonna have to handle this as well. Oh, but that's okay. Let's finish this code here. So for not blanking, and the other thing I learned about brightness is that it should be greater than or equal to 0 and also less than 128, I think it was. Less than or equal to 128? Yeah. Because anything greater than that, it's supposed to be black to be kind of accurate. Okay. And it is a float, right? Yeah. So if draw enabled, I'll do a little. Now this is really not the right way to do this line drawing stuff, but that's okay. We're gonna do it this stupid way, and then we're gonna worry about doing it correctly. Like one thing I'm thinking is, what I really need to be doing is I need to be remembering what direction our beam is moving in, and building one vector, one line for it, and adding that, rather than adding a bunch of tiny lines based on few number of cycles we're moving, which I don't even know if that's going to work or how bad that's going to look, but let's start with the simplest way and we'll see how it goes. So what do I want to do here? I want to build a line from the current position, oh yeah, to the target, which is basically the delta. So let's go like this. Plus delta. I need to implement plus with my vector. To operator plus. Left hand side, vector 2. Right hand side. And we'll create a vector 2 that takes x plus right hand x and left hand side y plus right hand side y. Okay. Okay. So now I don't have the shift register stuff done, so what's gonna happen is that, yeah, we're probably gonna get a mess because the shift register is extremely important because it will turn the blank on when it's finished shifting out the values in there. And if I don't do that, basically it's gonna draw when it's not supposed to draw. But I'm still fascinated to see what this will look like. Oh, actually, am I even using this? Instead of running in debug, I'm just going to run in release. So I'm not really getting much here. Looks like I'm not actually adding any lines, which probably means that drawing is not considered enabled. And my guess is because of blank. Or because integrators are not enabled? Oh. What's this? 275. Okay, so we're trying to execute an instruction that wants to set the interrupt enable flags. Okay, so I'll just continue from there. Oh, okay, that's interesting. Yeah, so I'm not really getting... So blank is true, so we're not going to be drawing. Brightness is 127, that's cool. And so, yeah, this has to do with the shift register. Basically, because I haven't implemented shift yet, blank is not set to false. Like if I force it to false, probably gonna get some garbage. But now at least we're gonna start drawing something. Or maybe. Oh, some little lines in the corner here. Oh, I've got a few lines in there. Probably, I'm not sure if you can see that, but there's this tiny white line here and a tiny white line over here. Alright, let me take a look at the shift register. See here. 8 bits used to set the pattern of the line to draw. When bit 7 shifts into bit 0 every 2 cycles of T2, which I haven't implemented. Timer 2 is basically that global timer. But anyway, when it shifts there, so it needs to run for 2 cycles of that. When bit 7 shifts out, it also sets blank to value of that bit. 0 means beam off, 1 means beam on. Upon write, shifts once immediately, which is useful for disabling the beam right away, not 2 cycles later. Right. Okay. Shift. So this is our friend here, the shift. Thinking about how to implement this. So let's do this. Let's add a little function. Shift cycle. No. Before we shift, we want to move that bit into ramp. No, into blank. I wrote here bit 7 shifts into bit 0. Yes, that's right. So actually what I really want here is to know what the bit value is. No, sorry, bit 7. We shift this guy left 1, and we OR in bit 7. And then blank gets set to whether this guy is actually 1 or not. And then what I'll do is when we write to shift, yeah. Don't like this too much, but date, shift. We'll kind of like fake a 2 cycle on this just to get the bit shift, the first bit shifted out. I really don't like this, but The other option is to move this out. Oh, and I need to actually call. I need to call the update shift in here. Hey, look at that. I mean, this looks totally wrong. And we now have a jillion lines. We have like 2 million lines. That's funny. But that's interesting, right? We actually see something. It's interesting because what I'm seeing here is like moving the beam to the corner. Down here to the left. It's very interesting. Yeah, it's interesting. I want to just remove this code here. Just want to take a look at some breakpoints to see what this looks like. Okay, so here integrators are enabled. What do my velocities look like? 0, 0. Brightness is 0. So we won't actually be adding any lines. Okay. So now we're writing 127. And then 128 into y. C0 into the x, y offset. Again. Then writing 127 to y, 28. So brightness gets a value now, 127. And then here we have y gets 39. So what's a ramp line? Alp143 asks. Basically, the ramp is an input line on the hardware that drives the beam, and the way it works is that, consider it like this: if the ramp is enabled, that means that the hardware that drives the beam will start to move based on the values that have been previously set in its integrators, its y and x integrators. So that's basically for moving the beam around. So ramp needs to be enabled, in which case means pulled low, hardware-wise, pull to 0. And the way ramp works is it's actually a bit that it's a memory mapped bit, and you can set it yourself from the processor, so you can actually turn it on and off from the processor. Or what's usually done is you let the timer manage it for you. So timer 1, as I was saying before. So you set up the timer, and then while the timer is active in one-shot mode, it's going to enable the ramp while it's active and then immediately disable it when it's not active anymore. So that allows you to say, I want to draw a line for this much time. Or even if you're not drawing, I mean, I want to move the beam. That's more accurate. I want to move the beam for this much time. And in terms of direction, I'm going to give you the x and y like magnitudes, the strengths to drive the x and y direction. Does that make some sense? Bit 7. Well, shift becomes, yeah, and then blank gets, did I do this wrong? Is it the other way around? Is it set blank? Oh, sorry, it's the other way around. Blank is if bit 7 is 0. Interesting. So Alps asks, am I self-taught? Pretty much. I started programming when I was about 17 years old. I mean, seriously programming. And I started with Pascal, and I basically had a book and I read through it and learned how to program from a book. And, after that I took courses and I went into programming, into computer science, but initially, yeah, self-taught from a book. Okay, that's more interesting. A little line in the middle of the screen. Let's go back into release mode. I don't know if that's more interesting, but it's not crazy lines all over the place. Have I heard of the RPG language? That's what you're getting trained for with your job? I don't think I know the RPG language. What kind of language is that? Low level, similar to COBOL, used mostly in IBM OS. That's kind of interesting. Why are you learning that? What is your company doing? Alp143 says, it's RPG freeform to be exact. Jack Henry Bank Software. I've been having some weird problems with my internet connection. There we go. It does look like COBOL. And a bit like BASIC. Like VB. So this is for bank software. I'm guessing if you're learning this stuff, for old software, you must be compensated well for that kind of work. That's usually what I hear. People that are, people that learn COBOL to work in old bank software, usually paid very well. Okay, so that's where you work. Oh, that sounds pretty interesting. I love this song. It's from one of my favorite games, Seventh Saga. You inspire me to learn C++ on the side now. Oh, great. Glad to hear it, man. This despite the fact that all we're getting is a tiny line on the middle of the screen. This is wrong. Still getting the same thing though. Okay, a few things I'm wondering here. Could it be that my signal is low? True. So many things that could be going wrong here, so I gotta check everything. Wait a minute. did I do here? That does not look right. Oh, that should be timer 2. That definitely won't work. Yeah, that's not something that would affect it too much. We'd only end up writing once to timer 2. Okay, so back to this. So writing counter low, 127. Actually, you know what I'm gonna do? I wanna see what the output looks like. I want this. I want color. All right. So we're at F1, F15D. So we go to the bias listing. Okay, so we're in the init via function. So this is to make sure that PB7 is enabled. Make sure that that actually happened. Yes. And now we are setting the scale factor that's in B to 7F. Correct. So that is what this is, 127. That's 7F, so we are storing that in here, which just writes to latch low. Okay. Oh, another write there. Interesting. F30E. Okay, so now we're moving. So we're in recalibrate. That makes sense. Reset 0 ref, recalibrate. So we want to recalibrate by storing B04. So what's in B? Load B FF 255. That's 255. So that means we want to put the highest amount of time into the time register. Okay. And now we're about to write timer high. So we're still in recalibrate. Oh, interesting. Yeah, okay, so by clearing T1 counter high, which is what we're writing here, this is supposed to, like, it does. I think it doesn't matter. That's it. We want to write a 0, and then that actually will say, okay, latch high is 0, perfect. And then here we're going to start the counter. It's going to be 255. Reset the interrupt flag. Since PB7 flag was set, the signal will go low. Right, okay. PB7 is really to control the integrator, so that makes sense. So this turns on the integrator. And now that this has happened, what are velocities set to? Yeah, I think probably what I'm doing wrong here let me see. Like the X register should be the last one that gets set. Move to IXFF, move to IXB, load BFF in there. So this forces the scale factor to FF. Set the scale factor to the YX position pointed to by the X register. Load D into X++. Okay. Oops. F310. Store Y into the DA register. So this is what I need to do. I'm gonna start all over. I'm going to stop at F312. We'll set a breakpoint there. Okay, so that's the timer stuff we did before. So there's our breakpoint. I just want to look at my registers. So, oh yeah, okay, so both A and B are 127, 127. So basically we want to move the beam, and actually if I recall, no, sorry, why are we moving there? I guess this is part of the recalibration. It's kind of like, we should see actually a load D. Load D, C83D, vec refresh low. Ah. Vec refresh, let me take a look at this. Oh no, sorry, that's the wrong thing. Okay, no, it's here. Load X, F9, F0. Let's go look here, F2, E6. Recalibrate. Recalibrate. Recal points, 7F, 7F. So there it is. It actually says it here, that the recalibration points are 7F, 7F, followed by 80, 80 in memory for recalibrate. So we want to move the vector beam to 255, 255 without drawing. And then to 80, 80, I suppose. Because I think, yeah, this function will take what's in X and increment it to the next value, which is 80, 80. 80, 80. $128, $128. Oh, this must be, okay, this is negative, right? Or not? Yeah, sorry, that's it. That's 127, 127, of course. So this moves it to the, basically to the bottom right corner and then moves it to the top left corner. Okay, so that's the point of this. It's basically making sure that the beam, if we move the beam to the bottom right and then to the top left in the extremities, it'll, I guess, recalibrate the hardware. Interesting. Okay, in any case, we don't draw those. I did not actually mean to make any changes, so where are we now? We're about to write 127. This is a very cool feature. Visual Studio 2017 actually shows you a snapshot of the code. If you've modified it by accident, but you hit a breakpoint, it shows you what the code used to look like. It's a pretty cool feature. So now we're getting a 127 coming from where? We're still in the recalibrate. Okay, yeah, that's the 127 we were talking about. We hit our breakpoint again. 128. So where are we now? Reset 0 int. This routine resets the integrators to 0. It leaves the integrators in 0 mode, so nothing can be drawn until a move is done, or D00C is set to 0xCE. F314. Oh, so we've already returned. So we're at F314. Move to D. So I see here that D was loaded with X++, which is, if my comment is correct, would be the first value would be 80. Yeah, which is 128. Okay, we're still in the middle of this code here. Yeah, we're doing the 80-80 move, then we do reset 0 ref. Okay, so now we're writing 255. So where are we now? Vector refresh. Okay, now recalibrate. We're doing another recalibrate? Really? Another 127, high. Disable that breakpoint. 128, high. Looks like, oh, okay, so now we are where we want to start writing text. Okay, so that's more interesting. Jump to intensity 7F, store A to vec brightness. Let's see where this is, F2B3. Okay, that's when we're storing brightness. Okay, that's to set the mux to the right channel for brightness. Okay. Return F046. Display power-up message. Okay, so that's where we are. Alternate size every 32 loops. Alternate size every 32 loops. So we load the address of double high text. Okay, so height, width, position of Y and X, so expect it to be at 27 hex CF with this height, this width. And it wants to write Vectrex. Bit A 20, branch if equal. What is expect to be an A? Oh, this value here. LF052. So it does go to F052. Print list hardware. Print startup text. This displays a group of strings described by the parameter block, which is pointed to by the U register. Yeah. And has the following format. Yeah. Followed by 00. So now we end up in print string HWYX. Load the U++, store the Vectrex hardware. No, not hardware, height width. Yeah. Which is stored in C82A. We had 0 there. F1, I think that's what we saw, right? F1? Yeah, F1 is the height. Does that make sense? Now we want to move to D7F. So we want to move to D7F. F2 to FC. Forces the scale factor to 7F and then moves the pen to the position specified in the D register. So there is a storing of Y. So here we write the DAC. Now we enable the mux, which means that it should write to Y here. Down here, okay. Store A04, counter low, so that's writes to the timer. And then this clear here should enable the mux. And that should enable, yeah, that will enable the Y, which will get whatever value we expect to go into Y. Why did this stop? Okay, that was weird. So here's the clear 0. So this is the part that should write 39. 39, is that right? 27, yes. So we're writing 27 to Y, which corresponds to here. And the next thing we expect is that CF should be written to X. It's kind of hard because if I put a breakpoint here, we're getting 27 for that Y, right to Y. Okay, this increment here. Okay, where are we now? F306, F318. All right, so we branch to here. Which loads a blank 0, 0 high, blank low 0 high, CE, yeah. And then store A to the control. Clear the shift register. So actually clearing the shift register should mean, yeah, it's all 0. It also means blank is true. That's good. Store X in the DA register. So here we are trying to store X into the DA register. Increment 0. Clear ink. Disable mux. Okay, so here we are disabling the mux, and then F5. $27. There it is. Okay, that's good news. So we are actually... Oh no, sorry, no, it's CF that I'm waiting for. So it's not good news. Store X, store B. Oh no, that's it. It had 27. And there it is, CF. Okay, so we are writing CF into there. So right now it's 207.39. Yeah. Yeah, 207.39. So basically X is 207 and Y is 39, and that's exactly what we see in our velocity. Now we're about to move our beam there by clearing T1 counter high. delay 1. Yeah, so we are in the middle of printing our string. We did a move to D7F. Then we have a delay 1. Then we have a print string. So now we are ready to print our string because we're in the right position. So we jump to print string. We store into U the vector string pointer, the thing we want to print. Load into X. Okay, so hold on a sec. Here. I'm going to start with charge and bitmaps. Okay, so we're basically in the print string function. It looks like we are, actually one thing I could check is what is our position right now? That would be actually a really good idea. Oh, and look at that, inf. Well, that's quite telling. That means we've got to divide by 0. All right, this could totally happen. So that could explain why things are not working out. Basically, I guess I should check if our velocity is 0, don't do anything. Oh, I did check for that though. But no, but that's not right because I'm subtracting 128. It's more like if the velocity minus 128 minus offset even would bring us to 0. That would be bad. Okay. Let's do this. What's not working here? All right. Let's go for the gold. Ah man, really hoping. At least my position is not infinity though. Okay, so I'm gonna stop here, and next week what I'll do is I'll continue in this function here, print string. I'll put a breakpoint here, not next week actually, in a couple days on Wednesday night. I'll put a breakpoint here and we'll continue to see if we are actually doing this. This is one of the more complicated bits of code, and in fact it's very possible that this can't work properly right now without the ramp stuff being cycle accurate. But still, I'm very curious to see how far we get. And in fact, maybe we'll skip this code and see if we can get to the... I know there's a draw box function that is probably easier even. What is it, draw box or something? Draw. Let's go to the draw functions. Draw grid, draw line. There's something about drawing a box. Oh, here. Intro boxes. There's an outer box and an inner box. This is a lot easier to understand. Draw the frame boxes. We're supposed to get here. So if we get here, this would be easier. Move to this, draw 4 lines, and we can see if this actually does what it's supposed to do. And this will be easier to understand than trying to understand the drawing code for the text, because the text stuff doesn't even use the timer. Let's see if we actually get here. I'll turn off trace. Oh, that's interesting. We actually don't get there. Oh, and then we get an exception. I know this one. This is the one we saw before. One thing is that my frame rate is dropping dramatically because of the fact that we're adding lines with abandon here. If I just disable this for a second, we come back and add a breakpoint here. So now our frame rate's much higher. Okay, we get that assertion. Interesting. So like it's as if we never come back from the print list hardware. Because see, if I put a breakpoint there on the print list hardware, do I get there? bit baffled here. How are we not reaching this? I thought we were reaching this vec title part. Didn't we just reach this before? Yeah. Oops. So we are at F000. First power up loop. This prints the Vectrex power on screen and displays the power on music. Yo, this is so messed up. I think what's happening here is this exception's messing everything up. Yeah. Yeah, 257. Let me just remove this for now. I think that's just screwing everything up. F4 CD. Still printing string. How do we even get here? Why am I not hitting my breakpoints? We should not be here unless we went to warm start. Oh, such an idiot. Not paying attention. I need to put my $sign to make it hex. Okay. Like if I'd say this way. There we go. Alright, so let's see now if we're getting to draw boxes. $sign. There we go. So this is draw boxes. So from here I can start debugging to see if we're actually doing the move and the drawing of the 4 lines that we expect, and then why that would not be working. So we'll pick this up in a couple days. So thanks for watching, and catch you on the next stream.